just keep going. Okay, it's my pleasure to introduce Dr. Manzil Zaheer. Manzil is currently a research scientist at Google. He received his PhD in machine learning from the School of Computer Science at the Carnegie Mellon University. His research interest is in developing intelligent systems that can utilize the vast amount of information efficiently and faithfully. His work has been at the interplay of statistical model and data structure, designing novel structure where compact representations of data, as well as organizing them for efficient access. Dr. Manzil now is in Google, and today he's going to talk about towards efficient and controllable ML by disentangling information and pattern recognition. Manzil, now it's your floor.
Yeah, thanks, Isong, for the introduction. And thanks for inviting me at MBZUAI. It's a great pleasure to be here. And I'm very excited to talk about our recent work, which we have been doing in making these machine learning more efficient, controllable, and so on. So it's like no big news that machine learning has come a long way, right? Over last 20 years, we have seen like some really remarkable results and on well-defined tasks like image classification or speech recognition. We have been like either beating human level performance or like at least being as good as on some set benchmarks, right? So all this is very good, but still there is a long way to go before we can use this machine learning in a robust way in some products, right? And why is that is I attribute it to the reason that these latest machine learning models, which are usually deep and deep giant models with a lot of parameters, are hard to control. And what do I mean by this control, right? If we think about it, there can be many aspects to controlling a machine learning model, right? So one may be like updating its knowledge, right? So consider, for example, GPT-3, right? It has been the latest, greatest NLP model with some really impressive results and demos people have been shown, right? And it's a generative model, so you can ask it to ask questions that will give you some responses and things like that. So if I ask it something about how does social distancing rules change or affect human behavior, right? And if you look at the output that this GPT-3 produces, it's something which not the humans will easily recognize. So it's like not talking anything about diseases, COVID, or all the like pandemic going around in the world. It's not surprising that GPT-3 doesn't do it, is because it was trained on internet data till October 2019. So, which is before the pandemic started, right? So then how do we like make GPT-3 aware of the new developments in the world, right? So some people can say like, oh, what if we just take these new news articles or new whatever the articles on the internet and fine tune GPT or continue its pre-training further. But it seems that's not usually enough, because if you start doing it, it might have some like catastrophic forgetting and affects its performance on some old tasks and things like that. So it's not as simple as just if I just continue training on some new data, it means it will easily incorporate it. So there can be other aspects of this controllability as well. So another thing is these point fixes. So what do I mean by that? Is these current systems are usually pretty good. All these like GPT-3 or other ways to do, say, question answering, it's pretty good. Like if I ask Google, for example, how many papers were accepted by CVPR last year, it will like give you out 1,400 papers. But it can be wrong also. If I just ask the same question for NeurIPS 2020, it somehow gives a really bad answer. Definitely more than 21 papers are there. And it can be sometimes even more embarrassing things can come up was it can even say like Canada became like a part of US, and it can say these kind of things which became like viral on Twitter. Right? And definitely we don't want these kind of outputs, but sometimes it's inevitable that these predictions will happen. But now how do we like fix it, right? As an engineer, if someone wants like, oh, this is the wrong prediction, we want to change it. And now if our model is like a deep giant model which is just predicting this answer, it's black box, there's not much things to do. And again, you can think like, okay, I will do some SGD fine tuning on these kinds, this question or similar kind of question. But if you start doing it, it does not only affects this question, but it might start affecting some other questions and its answers, and we don't know what are the consequences or the repercussions overall, right? So it's pretty finicky and not a robust system as much as it is. There may be further more aspects of what I mean by controllability. One things can be like computation, right? How much compute should be done for a given input value? So as you know, all these like models, these deep models are pretty large, but they are somewhat like very homogeneous in computation. So whatever input I give it or query I give it, whether it's easy, hard, always all these parameters will be touched. So every parameter in the neural network will be used for each and every compute or output. So that seems very counterintuitive or very different from how maybe traditional software systems are developed, right? Or in the human brain, like if I'm speaking, only some part of the neurons is getting used, or each activity, only some part of the brain is getting used, right? Not everything fires together. So there's this disconnect also, and some queries inevitably will like need more compute, more can be harder and needs more things. So if you want to tackle these kind of like controllability issues of a neural network, let's start by like understanding what these deep models are doing and what we can try, like how can we like solve them. So maybe the first question we can ask is like, why are these networks growing so large and being so homogeneous in its setup? So definitely it's not so hard to think that our world is actually pretty complex. It has many fine-grained aspects, context, everything. Like some input will depend on some in different context can have like different answers and so on. Like we need a lot of corner cases, lot of conditions and knowledge to be handled. So definitely we need a lot of capacity. And if you think one way to just increase this model size capacity is to increase the parameter count, just keep growing it. And it seems over the last couple of years, that's the trend, right? So starting from OpenAI's maybe GPT-3 or AllenAI's Elmo model, all the way to like GPT-3 with 100+ billion parameters have been getting used. Right? And one of the hypotheses, as I said, was like it's kind of just like using this more and more parameters to memorize or handle like this more growingly complex world. Right? And if the thing is this, if the goal is only to like memorize or handle this extra knowledge about the world, is this neural network the best way? Right? And even there have been some like theoretical work saying that in a world where there are like a lot of different behaviors, fine-grained clustering, and a lot of stale data, then memorization is somewhat like needed. There is no way around it. With certain assumptions, you can prove this thing, which was done by this very interesting paper by Vitaly Feldman. So then the question is like, yeah, if we have to memorize, like how do we add capacity? Right? So like what we have been doing is like, yeah, these giant models, which are, as I said, has suffered from some of these side effects, but although they're like very accurate, but what else can we do? Right? So there can be a spectrum that, on the other hand, you can think about these classical instance-based methods, right? Non-parametric like KN, and they have some very like desirable properties in it, right? For example, it has provenance in it. By that, what do I mean is, if you have, say, this is like my simplest representation of the data points, and here comes a query point, and I want to like predict what label it is based on its nearest neighbor. So it predicts this purple class, and we can just say like, oh, because it's similar to these other things, I'm predicting it's purple. So that's pretty good provenance it's providing. The other nice parts are it's very easy to add, delete, modify data. You can have like very efficient data structures for nearest neighbor index, which can add or delete points. You can even do some like things like point success rate, right? If say this was my query point, it predicted blue, and then some expert came in and saw that, okay, this doesn't make sense. So I can do like few things, either fix some labels or delete that point, and these things are all like doable in very efficient way, right? So these are the nice parts, but it definitely has some trouble with generalization, right? It can only look at some simple similarity cases, right? For example, it can't do compositional reasoning. If we have some set of like striped object cats, and we try to answer like what are striped cats, it might not be able to like combine these two concepts and say, oh, this is a striped cat. So the thing is like, can we do something in between, right? On one end, we have this cat models, which are not sufficient, has other problems that give some nice properties. Can we do something in between? And if you take like just think about humans, we usually are not like these instance-based methods memorizing or keeping around all these instances as it is, but we keep around some like bunch of skills and important facts, but then we also know how to look up new facts and make reasoning based on those, right? You can ask some other domain experts or look up it in Google and make decisions based on it. So looking from like based on this like inspiration, I've been trying to propose this idea of disentangling knowledge and pattern recognition. So what I want is some of this AI system to be able to ground all its prediction on some data. So given a task or given an input point X or query X, it should like do some reasoning based on some data, and all its prediction should always be grounded in it, just like in the simplest case is the KNN classifier, but we wanted to do in like much broader and more complex tasks. And so to accomplish something like that, what is needed? So for building such a system, we would definitely need to organize all this data. So we might need hierarchies, data structures to solve this. And also, once you have all these organizations, you need some very flexible modeling. You might need some like, how does like deep learning access all these memories, how to use it maybe in an online setting and things like that. And I've been working on both of these areas for quite some time. And I've been always like trying to ground all my progress in some application. And for example, in NLP application, you can think about like question answering and how all this progress help there. And today particular, I will talk about these two aspects. So in particular, what they are is this case-based reasoning is a technique to do grounded machine learning or grounded predictions for question answering. And it can operate both on text, knowledge bases, and we'll see how it does and how it does disentangles this whole reasoning from the knowledge part. And in order to do that, we'll need some tools, and we'll need, for example, to use transformers, which are the state-of-the-art methods for doing NLP, and how to like extend it for like really long sequences. So we'll cover mostly these two in today's talk. So without Machine, let's get into it. Right? So just to set up what's going on. So question answering, as all of you might know, is what happens is user comes in and asks a question like, which league did Colin Kaepernick play? Right? He's a basketball player and you want to know what he plays. So an AI system ideally would be has to like answer this. And if we consider these models like T5 or GPT-3, all these like giant deep models, what it will do is take this question directly using whatever knowledge is stored inside its parameter, try to embed out NFL. Or it might more like other kind of reading comprehension methods would do is like base like retrieve some kind of text, base read it and give the answer, or you can use knowledge bases to answer it. Right? And it might be each of these systems has like different pros and cons, right? So maybe let's start with how to answer it, say using knowledge base. So once you are given this question and for answering knowledge base, the first step is somehow like extracting the entities and the relation present in the question. So for now, let's assume we could extract out the entities Colin Kaepernick, and the question is asking like play which league played in. So in case of what knowledge base you do is like start from this entity, try to figure out what relations are there and based on it answer it. In particular, if this relation was already present, I could have just directly answered it and my work was over. Right? But the problem is these knowledge bases are usually incomplete. Right? They will never be complete. They won't have all the information. So to answer it, you have to do some kind of reasoning always. So you have to somehow reason why, given this facts, reason that why NFL is the correct answer. And how do people usually do it is, again, state-of-the-art methods are some neural methods. So they take in this question, they first form some embeddings because these are like words, discrete objects, and then give some neural network input and output will be this entity of NFL. Right? So the problem with neural networks, as we said, is these methods really do well. You'll get 90 plus accuracy on many, many data sets. But again, the problems are, as I discussed, is adding new data. And it can sometimes even hallucinate. It can give answers which are not even related to the things. So what can we do about it? So like similar to KNN, we wanted to like ground all these predictions in the knowledge base itself. So our idea was to treat this whole knowledge graphs as an environment in a RL kind of framework, reinforcement learning. So here, what happens is, given this question, we imagine that the agent say starts at the node corresponding to this entity, and at each time step, it has the choice of actions as to navigate in this graph. Right? So follow different edges, and these edges are like colored or has labels. So maybe figured out like to answer played in lane, I might have to like follow this link. So can go there and then every time like again make the same kind of decisions. And after some time it will like say, okay, I figured out this is the answer and I will commit this. So if we have a system like this, it will always like get a reasoning path and it's like well grounded in data, so it can't arbitrarily give any answers. So this is nice part. And how does it do in say some benchmark data set? So here we have on the x-axis like many different knowledge bases and some standard benchmark. The methods we are comparing are both like pure neural kind of methods here, and as well as some like symbolic methods. So symbolic methods will also give a provenance and will give a proof for why it's predicting some answer. But the problem with many of these symbolic methods are on these larger data sets. They are just, they don't scale. They just run out, like you keep running them, it doesn't get with any answers. So the neural methods are like doing very high accuracy, and Minerva is our model of this RL agent, which is doing. Okay? So you can see it's usually almost as good as all these neural methods, but also scales to these large data sets and can give like the provenance same as all these symbolic methods. So, and it's always like grounded in the data, right? So one limitation still people might say is like, okay, this RL framework, all these things are beautiful, but is it actually just limited to knowledge graphs? Right? Because maybe knowledge graph is, as we said, is incomplete and you want to handle text and things like that. Right? So to understand that, like, let's try to view what this agent actually learned in a more abstract way. So what it has actually learned is it has actually learned to do some like relation following. Right? So condition on the question, it's like trying to start from like whatever given entity or set of entities, follow to some relation, arrive at a new entity, and keep repeating this process. Right? And in case it was a crisp knowledge graph, then these follow or this action which it has to take was like a very crisp thing that, okay, if I start from say Mila Kunis in this question, I exactly know what to start in, and I can take like this very discrete or very crisp action and move to a next node and keep going on. But there's no need in particular for this to actually operate on this crisp knowledge graph. So, for example, you want to extend to natural language, what you can do is say, let's consider the case when we have some knowledge graph to see, but we have a lot of text also. So you can have say this knowledge graph to start, but also you have always say Wikipedia pages about these entities. So you can get sentences from Wikipedia which are entity linked, and you can have this new kinds of paths between different entities which are like textual paths, right? So you don't have a crisp relation sitting on top of it between these two, but they're only described by this sentence. So Macbeth and Family Guy are related, but we don't know exactly what relation other than this sentence. Right? So, but that agent in some sense doesn't need to know exactly what this relation is. It just needs some embedding or some representation for it to make that action or make that decision. So you can definitely use things like this. So what can we achieve from this? Right? So here we have like a MetaQA data set which has both knowledge based part, movie database, as well as the Wikipedia part. So based on, if we just use like full knowledge base, all the knowledge base, and use our previous method of that RL agent or any other like baseline, it will be roughly 90%. So that's good. But now if I delete say 50% of edges randomly from this knowledge graph, the performance drastically degrades. Right? So now the thing is, so this is a way to simulate like missing information and things like that. So now if we use text from knowledge base, like from Wikipedia, so 50% knowledge base plus text, our method is able to recover much of the performance. And in fact, so our method was called GraphNet, and there were some follow-up works by others who actually did more smarter way of like incorporating these textual nodes, and they could almost match the full knowledge base performance, which is like very nice. Other than like having even this seed KB, right? We can go one level far further and say like, suppose we have no knowledge base at all. Can we just use text and do similar kind of grounded things? And in fact, we can like come up with a virtual KB kind of idea where you are basically have to like store a lot of some informations nicely in a data structures, and you can again define this follow operator. you'll be, I won't be going too much into detail of how this is working, but it's basically storing some of these entities and how links and some nice sparse data structures, and you can run again this follow operator, which is differentiable and all the nice properties. And with that, we could now, like using text only, we could actually get 90 plus accuracy and actually match this full TB setting. And this is not only very good accuracy, it's also pretty fast. So here is like a live demo of it working. So you can ask things like, what is shape of the coronavirus? And as you saw, like it very on real time could answer it. But not only that, it could give this provenance. Right? So it just started from the entities present in this question, coronavirus. So looked at Wikipedia, first paragraph, what are the other entities present? So like coronavirus is present. So go there, there what is the sentence. From that, it could like figure out, oh, it's spherical. So we can, so it gives this nice whole path of how it's arriving at the reason. So in summary, what we have seen till now is like these kind of like a relation operator following, relation following operator. If we can define, we can get like a pretty accurate system, which is efficient, scalable, very fast, provides those provenance and can work both on knowledge bases and text. Right? And this approach like got us like in a EMNLP, there was a shared task on explaining question answering for fourth grade science questions. And this same, this again, this relation following kind of explanation, we could say like why these kind of science question, why is this a correct answer? So any questions so far?
So most of the question will be near the end, but I can ask some quick questions. And
yes.
Yeah, it's very interesting techniques. So have you ever actually considered trying similar idea on images or to understand complex scene? For instance, there may be common sense knowledge graph and Wikipedia and even structured knowledge graph. Is there a way to generalize the approach to understand complex scene?
So I think this idea is definitely applicable for images also. So as I said, this the how we are like moving from one state to another is not, it did not be something just like a played in or lives in this kind of relation. We can definitely come up with more generic reasons to move around based on image kind of properties, right? Whether it's in front, it's in back, where it's situated, it's contained in things like that. And we should be able to come up with similar reasoning pattern, like will this object fit in a suitcase? And it can come with similar kind of reasoning. So I've not tried it in particular, but I don't see it's like being impossible to do something like that.
I see. So there are also some method trying to, for instance, combine the deep learning component with just logic and reasoning engine. I don't know whether you see something called the deep problog. They try to combine this deep learning model with the problog reasoning engine. What do you think about those engines?
Yeah, so I think so. So I didn't compare directly the problog, but those are like very fascinating and good approach. But I think till now they suffer this problem of scalability on really large data sets. So this neural problog or neural EMQL and all these kind of methods, neural theorem proving, all these, if you have like a large number of facts, it usually doesn't scale very well till now.
Yeah. Okay.
That's okay. So we have been talking from at the start of the slide about controllability, right? A lot of them. So what methods have presented definitely has some nice properties about provenance and things like it, but did we actually achieve all like aspects of controllability? So in fact, till now, like this RL agent or the method which we are using is still like a deep network which is following in its all the like decision making thing, right? So given the current question, current state, wherever it is, it's still making which one to take is coming from a neural network. So it's not now very easy to like make changes to, okay, don't follow this path because either it's like maybe biased or has some other kind of wrong or has some problem. So if I want to do some changes like that, it's not like obvious, right? So I can't just say, oh, don't go do this path, this maybe is based on some gender relation, something which I don't want to. So how can we make that kind of controllability also inside? So for this, we'll go back to some like concepts in RL from like long time back in years 2008, it was introduced for like this episodic control. Okay? So it's a very intuitive idea where what is happening is you want to just every time if we are what action we have to take is just from our past memory or history, try to see like what is most similar to my current situation and what in that situation what we did which gave us good results. Right? We just want to repeat that. Like, and it's like somewhat motivated from our hippocampus systems. I'm no expert in biology, but this is what these papers mention. So, and like a very simple example is like if we are playing some kind of like a chess system and you had many past games you had and different situations, you know, okay, if I played this, I had good rewards with it. Right? So I saved basically a whole table of state action and some like rewards associated with it. Now, if you are playing a new game and you are in some state, what you basically do is try to find the most similar state and you look at what reward I got, and based on that you make the current action. So mathematically, like it's not just based on one, so you aggregate over your k nearest neighbors. So if you have k different states in past, whatever it's like q function or q value or reward basically is stored from that from that state taking that action in future what I get. So I try to maximize that and play according to that. So very simple. So and intuitive. So now if you want to like apply some idea like this to question answering, what do we have to do? The nice part of this is like it again is KNN kind of method. So again will be grounded in our data. And in particular, what we'll do is we'll try to come up with this case-based reason. So coming back to again, say this knowledge-based kind of setup where we have a question and we're asking, where does Melinda Gates work? Okay, so again, we look at the knowledge graph, find Melinda Gates associated facts. Now for like this episodic memory, what you do is you try to find what are similar things. Okay? So what you do is try to find similar entities to Melinda Gates. You might find people similar to her, you might get Bill Gates, you might get Warren Buffett, you might get Mukesh Ambani, people like that. So once you get these similar entities, you try to look at their neighborhood, their subgraph. So for Warren Buffett, you picked up, for others you picked up. And then what you see, whether in these similar entities you have the desired target relation. So for say example, in the Warren Buffett case, I have this available. So I keep all these relevant subgraphs where I have this. So now what we have is this target query and this memory bank of all the similar cases. And from that, you can like extract out some reasoning patterns that maybe CEO and headquartered implies that you work in that setting. And you need to formulate some like a nice probabilistic model about there can be like many reasoning patterns. So which one is a higher probability and so on. So I won't go into those details, but you get like a ranked list of all these reasoning patterns, and you can apply them now to your target setting. If say I take this one, I apply, and then I can do the prediction that works and see happens. So here, the nice thing is again, like along with this provenance, now this whole decision pattern is somewhat like in my control. So if it, suppose it figured out some path using protected NP relations, I can go and just say like, okay, we're not going to follow those edges, go delete that or put a blacklist and things like that. So very nice to control and things like that. And in practice, how does this work? So even though it looks like super simple, again, if we look at from last time, that we are only considering these big data sets, not the smaller knowledge bases, the same kind of neural models. This is the RL kind of agent. This is case-based reasoning. It actually does way better than anything else. It's better now, this time even in accuracy. It's really scalable. It's has all this provenance, and it's really grounded in data and has better controllability. And in fact, we can do something like quantitatively about it also. In particular, like we can now add or delete knowledge without affecting any other predictions. Because if you recall, these steps actually don't need anything which will get modeled. So if you want to add a new data, what happens is, say you get some new set of these relations or facts that over time you collected these new facts, now you want to add this. So what these might have is like totally new entities, this might have totally new relations which you have not seen before. But as long as you can produce some like entities for embeddings for all of these, you can always like add it in an incremental k-mean index and you're done. So that's about it. In particular, we did an experiment. So we took like the free-based knowledge base, and we were like incrementally adding data. So we started from 50% of the knowledge base, and incrementally we're adding 10% more, or 5% more. And here on the left is I'm plotting like the accuracy on a fixed held out set. So here the offline based is like constant because it has seen everything and it's doing prediction. And here the accuracy, as you see more and more data of some like the best, second best, like the state neural model, starts pretty good. All methods are pretty good, but it can have a catastrophic forgetting. Okay? So if you keep doing like SGD kind of update on the whole data is like maybe forgetting something old, but here on the right, what I'm talking is only test held out set of facts relevant to that time step. So here it's actually doing pretty well. So for any new thing, it's like learning very well, or it might be forgetting something from the past and things like that. So that's why its performance is hurting. Right? So, but you can say like very easily, like, oh, I will not, what I will do is I will freeze some of these embeddings of the old entities and will not change them. So you can definitely do that. So that definitely helps. But soon what happens, it starts running out of space where to put embeddings of the new entities or new relations. Right? So on the new things, it starts running out of space and start being wrong performance. Whereas these like non-parametric models like very nicely grow and adapt to incoming or increasing data, and is almost reaching the accuracy of the model in hindsight. This time, like with this case-based of reasoning, we can actually only be like not only be accurate, but also be able to do things like add, delete, control, and only look at few of the instances which are relevant to the current prediction task. So we're not looking at my whole knowledge base or whole thing, we're only looking at part of it. And that's why it's able to do with efficient, it's somewhat like disentangling this pattern recognition and efficient data structures for storing all this knowledge base together. And in our case, it was just this KNN setup and embedding or verification of the probabilistic model to do that rank test. Now, the question is, can we do it for more complex tasks? Right? So till now, what we saw, all these reasoning patterns are just simple chains. It's definitely questions in real world are more complex. Right? You can ask questions about someone's first book. So now you have to actually look at all his book and do a min over it and try to find which one is the first. So for doing things like that, simple this kind of path might not work, but like SQL or all this like structured query language can definitely express this. So now the thing is, how can we apply case-based reasoning on this, these kind of like more controllable approach? So our proposal is something like this. So we start with this question. You again find like similar questions in your training data set, some like big collection. So you get some similar questions. For that, you have its own semantic path. It's like query line, corresponding query line. So now, can we like use this question and its relevant parts to formulate the semantic parts for this question? We can like use parts of it, like first maybe, so it learns that, oh, we have to order by and select the first one, right? So sort it and select the first one, things like that. And this way it doesn't have to like memorize all these like different relations, these commands for doing things. It just needs to know, okay, these are the relevant things and I need to put them together and solve it. So in particular, what I'll do is like just taking another example about who is newly elected governor of California. So here I'll take this question, all these list of these different questions. And to do this selection and cut and paste, I will use like a transformer, say, to do this reasoning. But this transformer won't be a very giant model, right? It won't be 11 billion parameters, I think so. It will be a small transformer. But the challenge here is, since we'll have this like long list of cases, it won't be like one or two cases, right? You don't to retrieve that exact one or two cases will be very hard. So you want to like retrieve a list of such cases. So making that long list, so you have to like extend this transformer to handle long relations. So this is like a good transition to go into the next part, which is transformers for long sequence. How do you like design transformers for long sequences? So as we all know, like handling just these long sequences is a very generic task. I'm not going to go too much into its detail. But what happens in a transformer is basically this attention mechanism, right, which has been the bottleneck. So it's like a quadratic mechanism. So what you have is two sequences from which you like attend to each other. Right? These are the new concepts that was introduced in transformer, and which is basically its bottleneck. So why it's a bottleneck is because what you do is you start from the your two sequences, you create some auxiliary sequences called query key value, but you have to create this attention score matrix, right? So it's a query times key. So for each query and key inner product. So this is like if n is equal to n, this is like a quadratic size computation in both memory and compute, it's quadratic. And after that, you take a convex combination of value to get this output. So the important thing to note here is it's quadratic. And if you compare it to like previous state-of-the-art methods or before transformers, or came like RNNs, recurrent neural networks, CNNs, all of them were actually linear in the sequence length for both in terms of compute, in terms of memory. And to speed this up in transformer, it's like been a long list of papers have been doing. And there has been also some like benchmarks for establishing what is good or bad. So Here, for example, the space is like memory requirements and a metric of called LRA, long range arena. So higher the metric, the better performance. So here is this transformer with this full quadratic attention. And then there have been many ideas about the linear or some of the simple things, but they usually lose in performance for reducing this memory consumption. So we were thinking that can we do something better in this space? Right? And the idea was basically to look at this attention instead of as a matrix operation, look at it as a graph. So you have this sentence here doing this attention score, but you can think of it as like a fully connected graph. Then you can ask like some natural questions. So do we actually need all these edges in the graph? So in fact, what is this edges doing? Right? It might be doing things like co-reference resolution. It might be doing the subject object interaction, things like that. And you want like information to flow between different tokens, basically. Okay? And if you are familiar with graph theory or spectral graph theory, there's this concept of mixin time, which formalizes this idea of information flow. And complete graph definitely has a very slow mixin time, but there are many other random graph models which are sparse, uh, which means that there are only linear number of edges inside it, but has a very small mixin time, right? So in particular, Ardashirani, which is just a random graph, or a more interesting structure is this Watt-Strogatz model, right? Which has a very interesting structure, which also has very low mixin time. So what is this Watt-Strogatz model? This actually has two components. It has, you start with say a deregular graph, right? So which you can think of as a locality, right? So it's just everyone is connected to its neighbors. So the locality, and it has then some random edges connecting different tokens. So this is the adjacency. So random edges, this is like deregular kind of locality. And we were thinking like if this is all, can it do as well as transformer? And it seems actually not. On like mass language modeling or question answering or some entailment kind of task, there is definitely a gap between full attention transformer and these methods. So actually, we looked at like the proofs of a transformer and like why it's a universal approximation. Right? And why is it a universal approximator for all sequence to sequence functions? So the idea from there came that you need a few nodes which connect to everyone. So you need at least one node which has a global connection. So based on that, what we did, we modified Watt-Strogatz to have these global connections. And once if you have introduced these global connections, you can get like good performance. And we can actually prove all these things, like they are still these linear number of edges, they are universal approximator, they are Turing complete, and all these things. But I'll not go into detail of how these things work. And the nice thing about all these structures also, like apart from theoretical guarantee, we need like good implementation of it. And this whole pattern is on its own. If you directly try to implement it, may be bad for our computation infrastructure like a GPU. So we needed to introduce some tricks. And to quickly show you what these tricks are, so basically does some blockifying. So I'll go into some animations to show you what this is doing actually. So if you recall like what this attention is, it's just like doing an element-wise product between all of them. So it's this full matrix. But what you can do is you can do some reshaping to it. So I will convert it into a 3D tensor, in fact, and then do an element-wise tensor product. Right. So now if you expand it, actually it corresponds to exactly the diagonals of the full attention matrix. But if you recall, what we want is a deregular kind of like a locality neighborhood. Right? So just the diagonal or block diagonal is not good enough. So that's not too hard. So what you can do is say, like I just copy it over, and do a roll towards one towards left and one towards right, right? And then again do the same idea of 3D reshape and do matrix multiplication. So tensor multiplication. And now what you recall is that is a diagonal plus it's one offset on both sides, right? So this way you can get without doing any sparse operation with only dense operation, which are very good on GPUs. You can get these simulate these kind of sparse retention, and then you can add some random edges with lookup operations. So, like in particular, what we have been able to do is like to simulate this kind of like a sparse pattern, actually convert it to this dense packed tensor multiplication. So that way it becomes like super efficient on GPU. In interest of time, I will like skip some of these lectures and quickly come back to our setting of this long case-based reasoning where we had this question and we needed this long transform. On many of these data sets, you can see like compared to the T5 with 11 billion, right? Our model with a transformer of only 110 million parameters and some of these like cases, we are able to get really good results on many of these tasks. And in fact, you can do a human in the loop experiment also. That if suppose it gave a wrong answer, expert came in and added some like different cases in my database, and just no retraining anything, it will just start working. And you can have like a more quantitative analysis of it also, like you can do like compare with an SGD thing, right? So you can take a transformer working on it, try to do a few rounds of SGD. You get either like a catastrophic forgetting, like on the test, the performance reduces, or you can do some balancing, but then it's not as good. Whereas if we can just like add things into the.
So, Manzil, your voice is low. Can you somehow speak louder? Get closer.
Yeah. Can you hear me now better?
Yeah.
Yeah. So with our setting, what you have to do is only add these new cases into the nearest neighbor index. And this way, like no change happened in the original test, but on these new unseen relations or cases where we were wrong, it could just see like the performance improve a lot. So with this, I would like to conclude the talk. And in summary, like what we saw was there is possibility to disentangle knowledge and pattern recognition, right, in ML system, which can make it more accurate, efficient, controllable. We could achieve a lot of this in the particular setting of question answering, but maybe we need to generalize it further. But on the way, we will need to develop many new tools, right? It won't be just a simple neural network working. So for example, we had to develop this long attention mechanism, reduce its memory consumption from quadratic to B. Right. So that yeah.
Okay. So, Manzil, I have a, okay, you have a summary or?
That was, I think, the summary.
So your sound is
that is
become well. Okay, great. Yeah, and that very interesting, especially the knowledge base part and also transformer part. So nowadays, I've seen some work in the literature transformer, trying to use transformer for reasoning, and or even try to extract knowledge from transformer. What do you think about those work? And is there a way to combine those with your research?
Yeah. So I think I am actually proposing something to do exactly opposite to that, right? So if you in fact look at say GPT-3 as a knowledge base itself, there have been a lot of metrics to measure it. So it's good on things like who is president of US and facts like that. But if you ask any like a tail fact like about someone less popular, like then it starts like either hallucinating or it gives like weird answers out. Right? So it's not very crisp in that sense. Whereas if we have a dedicated knowledge base, we don't need these large language models to actually store all these knowledge, because it's not easy to store it. Then there are these other kind of effects also. These language model, when you try to use it as knowledge base, happens is many of say in the swimming, for example, this happens with T5 models. So many of swimmers who are world champions are usually Olympic medal winners also. And if you ask sometimes like some swimmer like which competitions he won, like he definitely won the world champion, but it will like add on like he also won Olympic gold medal in this year. That are like not true facts, which are not grounded in like real data. So that's why I actually don't want to go in that direction. I'm saying things are inefficient and it's not the best way to store knowledge. We have over the years in computer science developed these nice data structures to store things. So instead we want to like give transformers some mechanism to access all these like efficient knowledge graphs or knowledge, whatever store you have, some index, and use that to make the predictions. Sorry, you are muted. Please.
So nowadays, transformer are also very popular computer vision, right?
Yeah.
Do you imagine some of the idea you presented here for efficient transformer could also be used in that setting?
Yeah. So all these, this idea is like very generic. It's general purpose universal approximator. In fact, some of the baselines which I here, like linformer or linear transformer, performer, they have actually been not used in NLP tasks. They are not really good in NLP tasks, but they are pretty good on kind of like vision tasks, like reformer and all of them. So I would imagine, because I think the NLP tasks are harder for transformer, you have to actually use particular interactions, whereas in vision there is a lot more redundancy in how those interactions can happen. And that's why many of these approximations actually work pretty well in vision. So I would imagine our proposed method, which has like a good trade-off in this metric and memory, should also work very well for vision tasks.
I see. Have you looked into multimodal kind of data analysis, for instance, image with caption or video with sound or caption, things like this? And what do you think about those?
Yeah, those are like really interesting areas, and yeah, I have not actually worked with them directly, but yeah, if we want to have like at end of the day an agent which is interacting with humans, really it should have all this multimodal modality, right? Speech, vision, text, all together. But and all these like methods definitely should work there also. Just I've not applied them directly.
Right. Yeah. Thank you very much for the answers, and also thank you very much for the talk. And I believe that there will be a separate session with the faculty, and they will probably ask more questions, and we will meet each other in that second section. Yeah. Okay. But for now, thank you very much for the talk. Thank you. Yeah. See you soon.